I
Yes.
have a quick question.
Yes.
On one of the homeworks, there was a problem that gave you a y equals x plus b equation.
Yes.
And then it gave you two coordinates, like 2 points, which were like -9 and 9.
Okay.
Like, and it was asking if these like points were like a solution to
Yes.
the problem. In that case, do I just plug in like the y and the x
Exactly.
and see if they solve? That's how you plug it.
Right. If you plug in, if you're given a y equals, if you're given an equation with an x and a y, and you're given a coordinate point with an x and a y, you plug in that x and y into and it makes a true statement.
That
Okay?
means it's
That means it satisfies that function. It is a point on that graph.
okay.
Yeah. And if it doesn't, it makes a false statement, then it's a point somewhere, but it's not on that graph.
Yeah. Okay.
Okay. And if you have the specific number, you can send an Ask My Instructor, and I'll look at if you're having,
Okay.
And this is for anyone. Ask My Instructor if you have any questions at all, simple or complex. You're like, I'm not even sure, like I kind of got this problem, but I don't understand why. Whatever. Okay, you could send me questions, and that way I can sort of deal with them a little more in real time.
Okay.
Yeah, not real time if it's 3 a.m., but closer to, yeah. Okay, good. Other questions about homework or concepts? Okay. So where we left off was looking at some applications. Okay, we looked at function notation, understanding functions, and how they actually help us in real-world situations. Lots of things in the sciences, social sciences, hard sciences, medicine, etc., are modeled by. You need functions to model situations like dosages of medicine, or understanding, in this case, in anthropology, or this is a forensic scientist studies bones. And criminal sciences use that. All sorts of fields will use the functions to understand past situations and predict future situations. Because when certain real-world situations follow certain relationships, they can be modeled by functions, and you can use those functions, like I said, to predict or to find older information. It depends sort of on what family the function belongs to. The ones we're working with are primarily in the linear family right now, meaning that these real-world situations that we're looking at are linear relationships. If you graphed this function, it would make a line on a graph. Okay? Different sorts of situations involve different families. Quadratic relationships we're going to look at more this semester as well. Quadratics make parabolas, and even especially particularly an upside-down parabola. If you are standing on the ground and you throw a ball up in the air, it's going to follow a parabolic path and then come back down and hit the ground. Okay? So a lot of things in physics, like projectile problems in physics, are modeled by quadratic family functions. Okay? So that's where we're moving to. Okay? We're looking specifically right here at linear functions, something that's modeled by a linear relationship. Okay, so the forensic scientists are using these two functions. You're given two functions in this case. Okay? And no matter, you're going to see a couple problems here we're going to look at, another variation of this in a minute. You're going to see several on homework. Basically, you are dealing with x and y values, two variables. Okay? Two variables that are connected in some way. They have a relationship. Hence, they form pairs, x-y pairs. Okay? When x is something, y is something. When x is something else, y is something else. Okay? And this function marries those pairs together. It creates that relationship. Okay? So your job, no matter sort of how wordy or what it says or what the subject's about, even how your function is written, some of them are written as y equals, some of them are written in standard form. Okay? But you have an x and a y, and your first job is to think, okay, first I need to understand what my x and y stand for. So your first job when looking at these problems is to understand your two variables. Let's just look at this first one, the h and the f. Okay? So we want to know our two variables, f and then h of f. Okay? And our first job, and it's going to tell you in the problem, you need to read through the problem and figure out what does f stand for and what does h of f stand for. Okay? So we got forensic scientists. They use these functions to find the height of a woman if they are given the length of her femur bone, f, or her tibia bone, t, if we were going to be looking at the second one. Okay? So what does f stand for? Right. And specifically, right. So length, and I can put in centimeters. okay, of the femur bone. Now, if they measure a certain length of a femur bone, what is that going to tell them? The height of the woman, right. So we got height. Often the letters that are used, instead of X and Y here, or F of X and X, a lot of times you'll see letters used in real world problems that sort of match the things you're talking about. So in this case, F is not the function, F is actually your X value. Okay. And this H of F is your F of X, or your Y value. And that's the height of the woman. Okay. So, what depends on what is one thing to think. Okay. Right, the length, or is it the other way around? Height depends on the femur. Right. So our independent variable is the F. And the height of the woman depends on how long her femur is. The longer her femur is, the taller she'll be. And so that is our dependent variable. Usually the one we plug in, our X value, is our independent, and then we get the value of the function, which is our Y value. So dependent. If you think of it sort of like on a graph, an XY graph, but in this case, our X-axis is F. Oh, there we go. And our Y value, or the value of the function, is H of F. And as the femur gets longer and longer and longer, then the height of the woman gets taller and taller and taller. Okay. That height depends on F. So you've got your independent variable, which is generally your X-axis, and your dependent variable, which is the value of the function, which is your Y-axis. So your first job, no matter how these problems are worded or how your function is written, is to figure out, I've got two variables, and what do they mean? The problem's going to tell you what they stand for. Okay. And then the second thing, when you're then asked a question, is you're going to be given one thing, and you have to find the missing thing. Okay. So there's two variables, and in most of these questions, what you're being asked is, here's one thing you know, so based on that, what's the other thing? And your job is to figure out, okay, what if they told me, what do I know, and what's the missing thing? Okay. So let's look specifically at this one with the femur. The other one's about the tibia, but let's the femur one. So we're asked to find the height of a woman whose femur measures 46 centimeters. So out of femur and height, what are we given?
46.
Right, which stands for F or H of F? F. So our femur is 46 centimeters. And what's unknown, because that's literally in the question, find the height, which means we don't know it. Okay. So we know the femur, but we don't know the height. So identify what your two variables stand for, and then write your two variables again and fill in the one you know to figure out which one's missing. Now, what we don't know is the height, so we take that, the height's unknown, but we do know the femur is 46. So we want to find what is the height when F equals 46. So we're trying to find H of 46. Okay? And so that function is 2.59 F, so we plug in that F, that 46 for F, plus 47.24. So the height of the woman who has a 46-inch femur is 2.59 times 46 plus 47.24. Now when you don't know the value of the function, you know your X, but you know your X value, your independent variable, but you don't know the value of the function, then it's real simple at this point. You just plug it into the calculator. Okay. You don't have to actually solve for something because everything is, these are just numbers on the right. You're already solved for your value over here. And you can use the store button if you want to store 46, but this is really just basically one entry, so it's probably just a little more efficient just to enter it. 2.59. I enter it just like I plugged it in, parenthesis, 46. Close the parenthesis, plus 47.284. So the height of a woman with a 46-inch femur is Make sense? And the second one, I'm going to move on to the next problem, but the second one is the exact same setup. The height of a woman whose tibia is 35 centimeters. In this case, you know that h of t is the height of the woman, where t, your independent variable, is the length of the tibia instead of the femur. And when you plug in the tibia that you know, you'll do h of 35 equals 2.72 times 35 plus 61.28. You just use the other function. Make sense? So I can fill in that as well. Like I said, these ones that we don't do directly in class, if you like to go back and practice, once I scan this in the next couple of days, anything we didn't do in class, if you did, you can go back and check your answer. And then let me know if you are confused. Okay. So let's look here at this one about tuition. Okay. So the subject of this function is about being able to determine the yearly cost of tuition and required fees for this public four-year college. Okay? And specifically full-time, so we're not worried about how many classes you take. This formula is going to tell you basically about how much this college tuition goes up over time. Okay? So you need to know, here's the function that tells you how much it's going to cost. We want to know specifically, now this function is named as f of x, so we know that we're going to have our x value and our function value, or our y value, or function value. Okay? So first we want to know what two variables are we working with? What does our x stand for in this function? All right. Now, see, we can't do math. These are the ones that get a little tricky. You'll see a couple like these on homework, too. Because we can't do math with an actual year. Okay? It's not like a year isn't a number on a number line in the same way, we can just plug it in and add or subtract it. Okay? It's numbers, but it doesn't mean the same thing as working with our math numbers. Okay? So we have to have a stand-in number when we're working with time. We have to have a starting year, and then x is everything after that year. So 2000 is going to be x equals 0. Okay? And so 2001 is x equals, and 2002, and so forth. So we're having stand-in values for x. Now, it's nice and clean and easy when they say the start year is 2000. Sometimes it's not that, it's like 1970. Okay? Well, basically, you're just subtracting or adding from that year to find out what your x value is. Whatever the year is given is x equals 0. And everything after that is 1 more, 2 more, etc. So x is time. It's specifically years, as it says, number of years since 2000. Which means, just as I said, x equals 0 is the year 2000. And so each year after that is x equals 1 is 2001, x equals 2 is 2002, so forth. Just be careful if it doesn't begin in 2000, because then you have to do a little more adding and subtracting. Now, what is f of x, the value of the function, or your y value? Right. So to sort of visualize this, in this case, what is our x-axis, our independent variable? Yeah, x, and that is years. Yeah. And so the cost depends on how much time has passed. Each year that passed, what's happening to that tuition? It's what? Going up. Yeah, it's getting higher, it's going up. And so here is our y value, our f of x, which is cost, and this is time, or years. Okay. So over time, tuition is going up. Okay. By how much? Take a look at this function. How much per year extra is tuition going to cost from year to year? Yeah. 318 exactly, because that's the one that is per If X is years, then it goes up 318 per year. Right? Whatever's next to that variable there is going to tell you how much it goes up each year. Now, if we're just looking at it's just an equation without all the other words, what is that 318 mean if we were to graph this?
The slope.
The slope, exactly. Slope is rate of change. Rate of change. That's how much it goes up per year. That's going to tell you how fast or slow that line climbs. Okay? And this is just a flat fee. That's sort of your starting point. Okay? So back in year 0, how much did this college cost for a full-time student? Right. Because in 2000, which is year 0, X is 0, then 318 times 0 means it goes away. And the cost of the college was $4,467. But each year, the next year, it was how much more? And then 2 years later, it was 318 times 2 more. 2003, it was 318 times 3 more, whatever that is, plus 444.67. Okay. Okay. So that's your rate of change there, and we're going to explore that a little bit more after this. All right, so you've made note. It's told you what your variables stand for, and so when you're being asked questions about it, you know, well, I'm going to need an x and an f of x, and in order to solve a problem, I'm going to be given one of these things, and I need to find the missing thing. So when we're using this function to approximate the yearly cost of attending this college in the year 2016, which piece of information are we given? X or f of x? X. X is what? Which is just 16, right. X is 16 based on the year 2016. Because we have to do whatever that year is minus our starting year. And then we'll find our X. Okay. And what we don't know is approximate the yearly cost. So that cost is unknown. That's what we don't know. So you have to be given one thing to solve for the other. You have two variables, but you can only solve a one variable equation. So you plug in the thing you know. So we want to know the cost. The value of the function is going to tell us the cost in the year 2016. 318 times 16, plug in anywhere you see x, plug in 16 plus 44.67. So in 2016, it cost how much money? What was it?
9,500.
Right. Yes. So you just multiply those and then add that. 9,000. What was? I'm sorry. I'm not 555. Right. Yeah. Okay. There we go. So the value of the function or the cost in that specific year, plug it in, and you get that cost. Now here we're asked using the given function, same function, to predict in what year the yearly cost of tuition and required fees will exceed $10,000. So it will be at least $10,000. So what out of x and f of x, what do we know? Right. Right. So if we plug in 10,000, we're going to see what year it got that much more or more. Okay. So once it hits 10,000, so we can just do equal 10,000, but that way we know after that point it's more than that. It exceeds 10,000 because it's going to keep going up. And what's missing? It's literally what the question is asking. It's what's the year? I don't know. Well, that's the time. The time is missing. We don't know. We know the f of x, so that's what we plug in for the function. And then we don't know x, so we write 318x plus 4467. Now, when we know the x, all we're doing is plugging into the function. You can see it's just number. We just plug that in the calculator, and we're just simplifying those numbers. If it's the function value we know, but we're missing x, then we actually have to solve the equation. Okay, we have to solve for x. So you got to do the minus 4467 on both sides. Okay. Get 318x is equal to 5533. Divide both sides by 318. Just linear equation solving. And we get x equals, and it's a long decimal when you enter it in. So I'm just going to, when you have squigglies like that, squiggly equal sign, that means approximate, because I'm just going to round it to 17.4. Just so I can see what my answer, I just did a quick round. That's not an exact answer, okay? But it's asking, though, it's not asking, if you put 17 or 17.4 or even that whole long decimal, you wouldn't have the right answer. Because the question is asking, in what year? Well, we solved for x, but what does that x equals 17 point whatever equal?
2x.
Right. So in 2017 is the answer.
Why is it 2017?
Because you add that, because the x is the year since 2000. So we can't use years for our x's. Yeah. So if our x is 17, that's 17 point something years since the year 2000. So we add whatever our x is to our starting year, and then sometime in the middle of that year is when the cost, so you might more technically say 2018, is when the costs have exceeded $10,000. And the difference here is what are you given? If you're given the x, you just simplify to find the value of the function. Plug in that for x and simplify. If you're given the value of the function, you plug that in for y, and then you have to solve for x. But then also make sure you have answered the question asked. Because in a real world problem, like for example, your x is 17.4, but x is the year, you have to do that little extra, what does that mean in the real world? Or if you get a decimal answer, but you're talking about like number of people, well, you can't have a partial person. So you have to make sort of some real world rounding so your answer makes sense and answers the question given. But that's basically it. No matter how wordy they are, how they're worded, what their subject is, what letters they choose to use for the functions, whether you're given a function in function notation or if you're given it as y equals, and there's a couple in homework you're given as standard form. Doesn't matter. You've got an x and a y. Define, pull out of the problem what your x and y stand for, and then each question figure out there's two things, I'm given one, plug it in the right place, and solve for the missing thing. What do I know? What's missing? Plug them in the right place and solve. Make sense? Make sure to try those in the homework, and then so you'll have questions ready on Thursday if you have any problems with them. Okay. So let's keep looking at functions and sort of real-world applications of them and what they mean. Specifically, we're narrowing down to like really looking a little closer at slope as well. And put this aside. These other ones, like I said, I'll sort of finish up anything we didn't get to in class, and when I scan these in the next couple of days, you can go back and check if you wanted to do the others for practice. Okay. Okay, so one of the handouts you have has these two quadrants on it. Y'all are reminding me I need to go get my flu shot. It sounds miserable. All right. Okay. So here's a basic situation, kind of a real-world situation, simplified, but it really is going to really point out some of the concepts I want you to be really, really comfortable and confident with. Okay. So let's say we've got a cab, some kind of rented car or Uber. Okay. So you've got a cab, and this cab is going to charge you as soon as you get in the door. You haven't gone anywhere. You sit down, it says where you want to go. But just by getting in the cab, there's a flat fee. Okay? So the cab charges a $2 flat fee. You haven't even moved yet. That's F-E-E fee. Okay? Plus, once you start moving, you're going to have a mileage fee. Okay? And that is, in this case, a $3 per mile. Okay. Now that per gives you a clue. That per means you got what's going to determine the cost of this cab? How many miles, right. The cost of the cab depends on how many miles you go. And each mile is going to cost you $3. Okay? $3 per mile. Okay? Now, this is that rate going to change in this case? No, not with the information I've given you. Sure, there are sometimes you can hire a cab. It's like, well, if you go 10 miles, it costs this much, but if you go more than that, it's going to be cheaper or more expensive. Those are called variable rates. Depends on how far you go. But this one, no, it doesn't matter whether you go 1 mile or 100 miles. It's $3 per mile. Okay? So this cab has a constant rate. It's constantly $3 per mile. It's not changing. So if we end up graphing what this cab charges, what kind of graph is it going to make? Yeah. Right. Is it going to bend or curve? No. It's going to make a straight line. This makes a linear relationship. This particular example is part of a linear family. As I mentioned earlier, there are other families that have different real-world relationships that make different shapes on graphs, but this particular one is making a linear relationship. And the reason it's making a linear relationship is because it has a constant rate. Each mile is going up by $3, and that rate doesn't change. And so that affects what aspect of the line that it makes? The slope, exactly. How steep that line is. And the steepness won't change. Okay, so if we were to both graph this and write its equation, let's start off by defining our variables. So x and y. Okay. So I already said the cost of how much this cab costs is dependent on miles. Okay. So our independent variable, which is generally our x, is miles. Okay. And that's our independent. So let's make that our x-axis. Okay. So x is going to be distance, or miles. And as our distance increases, what also increases or decreases? The cost, right. So that's why our cost is going to depend on how many miles we go. So y is our cost, and x is our distance. Cost being our dependent. We asked the cabbie, how much is this going to cost? And he's like, well, it depends on how far you want to go. Let's go ahead and just to get some increments on here. This, of course, is 0, 0. In many real-world situations, you're dealing with just the positive quadrant, positive x, positive y. I mean, you're not going to end up owing the cabbie money. Or no, he's not going to end up owing you money, I mean. You're not going to go negative distance. So you're staying in the positive quadrant, quadrant 1. Let's go ahead just so everything will fit on the graph. And our cost, let's label by $2. So $2 increments, 2, 4, 6, 8, etc. And distance, let's label that in 1 mile increments. So 1, 2, 3, etc. Yes?